All right, good day, everyone. My name is Chuck Swain, and I'm here for the next talk, and it will be on the Time Appliance project. But specifically, I'm going to talk about something that is adjacent to that, and that is P1952 IEEE standard. But before we get into that, I will kind of bring up why the standard is important. And from the government's perspective, GPS is a great thing, but it is a single source of failure. And they are really interested in resilience. And so they are pushing that. There's something called an Executive Order 13905 that specifically says critical infrastructure, which IT is one of those sectors, needs to have resilient PNT. So what does resilience even mean? And that's where this IEEE standard is coming into play. So it has been around for about 2 years now, and its goal is to enable innovation through collaboration. We're trying to have an open standard to define and scope what is resilience. It provides the technical standards and some of the aspects that will help innovation by having an open standard that we can operate off of. Now, this is matured to a state enough that we can, we have enough definition in what resilience means that we can have different kind of layers or different scopes of resilience. So if you have just your heating and air conditioning that needs to be synchronized at the time of day, that could be just a GNSS receiver, something really easy and cheap. But if you have it on your core system at that level where you really need that as your primary, timing is critical to that operation, you might want to invest more in a full resilient system that has multiple inputs, has real-time failover, and also does integrity checking amongst those, that kind of stuff, right? So again, that's P1952, and that is an IEEE standard, so it is open to everybody. You can attend the meetings, go to the IEEE website and search for it. It's free to attend. You don't have to be an IEEE member to vote. Just attend a certain number of meetings and be consistent in that so that we have a quorum. Again, so that has defined resilience and what it means to have resilient position, navigation, and timing. We're focused mostly here on timing, and that is mostly applicable here because data centers aren't moving. But if we're looking more at location-based services, maybe those position and navigation informational needs will be also part of that. But right now, we're just looking at timing. So again, it's matured enough that we're starting to look at what kind of testing would need to be provided to make this a tangible standard. And that way we can have collaboration and work on that. I will zoom through, this is the next talk, I'm sorry. So I do have a website and emails that I will find in just a second, but the 1952 standard is now having what's called ICAP, so that's a testing and conformance process. And this is where I'm looking for the broader user community that's not so timing focused to really help with us and understand what your use cases for timing are so that we can develop testing standards to that so that you could go to a Keysight or a Spirent or one of these testing providers and have a configuration that you could run to understand how resilient you are, how resilient the vendors that are supplying you that stuff, what that's really providing for you. In addition to performance, also have a resilience capability on top of that. So I'll pause for any questions, any concerns, anything like that. Cool. All right, so again, after the next talk, I'll put up the email and the website if you guys are interested. And again, it's all free, open standards. We're really looking forward to your guys' input. Thank you.
Okay, thanks, Charles. And so now I'm going to talk along the same line, but I'm going to discuss about the wireless precision synchronization. So that's sort of new thing, and I'm going to talk why it's important even at the data center. So suppose you want to, it's your world is, of course, the data center is the starting point, but eventually you might have the application that includes the user experience. And for that, there is a user with the handheld device. And as long as GNSS is in place, all the clocks are synchronized down to at least 30 nanoseconds or better with some technologies, and down to nanosecond possibly. But I mean, of course, there is a sort of threat to the GNSS, and when it doesn't stop operating, then the clock at the RU and clock at the user won't be synchronized anymore. But we have technology called PTP, which gives you a microsecond to 10 nanosecond accuracy. And also we have White Rabbit that goes down to sub-nanosecond. So the RU is synchronized still, but still user isn't synchronized. So there is a technology that we have developed that is you basically do the wireless synchronization at sub-nanosecond regime. And well, if you want to connect, the bottom line is if you want to do something with the user, then you need to synchronize your user device. And what I'm going to show is that virtually any wireless communication device can or should synchronize the clock at picosecond level. And so this is the sort of prototype of the module, and it uses 920 megahertz wireless communication module with the Gaussian frequency shift keying, and it's fully compatible with 802.15.4. So it's just you can send and receive the messages. But now, and it can range over 100 meter or 5 kilometer, depending on how much power you can put. And with the 20 milliwatt, it can reach 100 meter easily. And it can synchronize the phase jitter to 16 picosecond, which is sub-nanosecond. And at the moment, synchronization is at 35 nanosecond. So I show you two more videos. That this is to show that before we synchronize, the frequency at two modules are different and shown in this oscilloscope. But as soon as you start to synchronize, those two were synchronized over the air. That's one thing. And another thing is that actually once you have time aligned, you actually have the position and navigation almost as a byproduct. So this is the demonstration of using the same wireless module, putting two modules on the helmet, and then, sorry about the Japanese letter, but and two modules at stationary position. And we get the ground truth of measurement by using the laser range finder that you see at the construction site, at least in Japan. And so my colleague who developed this whole thing is wearing the helmet, and on the left is showing the synchronization with wireless synchronization, and on the right is with the laser range finder. As he drives around this electric cart, both real-time measurement has been done, and they are basically measuring the same thing. So we have actually made it small enough so that it can be loaded to the time card that is developed by the Meta with the open collaboration on this OCP TAP. And what we can provide here is that normally GNSS clock is given to time card, and there is atomic clock to back up in case GNSS doesn't work. But also this provides another path to compare the clock with each other through the wireless communication over the air. So that gives more path, meaning more resiliency to the time synchronization. So in summary, I have sort of introduced the resilient synchronization. And also we have TAP, Time Appliance Project, exhibition booth right behind you. So please visit us to talk to us. And also there is a seminar track for the TAP starting at 12:30, and I don't remember the room. But please visit us and let's discuss more. So thanks for your attention.